Hello, Riles. For lesson 4.9, I want to guide you through the construction of the diagrams. Often students say about word problems that once they have the sketch, they're able to do the mathematics. Um, I want you to focus on the fact that interpreting the problem and drawing the sketch is part of the mathematics and is part of the expectation here. So practice that part carefully. In the first example, we have a prison tower. Go ahead and assume that any building is perpendicular to the ground unless otherwise stated. I suppose I could have made that clear. It has a spotlight at a height of 60 meters. There's a vertical height. It projects a cone of light down to the ground. The angle of depression to the top of the cone is 18 degrees. My diagrams don't need to be to scale. I just use them for references. This angle of depression is measured from the horizontal, very much like related acute angles, always measured from a horizontal axis, not a vertical. Here's the angle of depression to the top of the cone. The angle of depression to the bottom of the cone is 21.8 degrees. Strange choice, but. And then the cone itself makes not a circle on the ground, it'd be a projection of a cone onto a surface that's not perpendicular to the cone. So you end up getting this ellipse, and we're looking for the width at its largest spot. So that's actually the unknown in the question, which I believe I called x in my solution. Okay. From here, I think I suggested using two right angle triangles. It would be a good idea to have these labeled A, B, C, D so that you can make reference to working in triangle ABC versus triangle ABD. And I think the argument was we find the length of BD, which I called Z, and we subtract the length of BC, which I called Y, and that's probably the easiest way to get our length X. There is a way to solve this problem using a cosine law in here, but it's more work than is required. Also, if you're not using primary trig ratios, like the tangent ratio in a right angle triangle, if you're using the cosine law and the sine law in a right angle triangle, you should get the right answers, but you are demonstrating a lack of understanding of primary ratios. So make sure that you are using the most efficient approach. I don't want you saying, I can always use the sine law because it always works. Okay, check your work on that one and compare it to the example. The second question, with the destroyer and the carrier hunting an enemy submarine. It says a destroyer and a carrier hunting an enemy submarine. They are 10 kilometers apart with the carrier at a bearing of 20 degrees from the destroyer. So I'm going to draw myself a rose, a compass rose. These are your cardinal directions, north, east, south, and west. The bearing of 20 degrees will be north 20 degrees to the east. And it said that the carrier is at a bearing of 20 degrees from the destroyer. So that angle right there is 20 degrees. And we know that distance is 10 kilometers. Okay. The destroyer detects the submarine at a bearing of 70 degrees. Bearings measured from north in a clockwise direction, 70 degrees, would be somewhere in that direction. But they don't know how far away it is. Let's label that angle there, 70 degrees. The carrier detects the submarine at a distance of 8 kilometers, but can't determine a direction. And I mentioned in the lesson that the sketch, a relatively accurate sketch, should show you the ambiguity of this situation. This submarine could be further away, or the submarine could be closer to the destroyer. And if you don't like depending on your sketch to do that, you're going to have to depend on your sine law and your understanding of the ambiguous case of the sine law. Let me show a full solution here. I'll say that angle CDS is going to be 70 degrees minus 20 degrees. Make sure you're labeling which angle it is that we're discussing, because there's a number of angles at D. You can't just say D is. I suppose you could introduce a Greek letter and use that. That's 50 degrees. If you feel like this diagram is a little bit crowded, I would agree with you. Let's just tidy it up. 50 degrees, 8. And we're looking for the distance in between them, but to find that, I'm equipped to use the sine law to find this angle. If I find that angle, then I can find that angle and then use the sine law to find that side. So let's do that. We'll call that angle S now. And I'm set up to say the sine of S divided by 10 is going to equal the sine of 50 degrees. Still on screen, not so much. Divided by 8. Strongly suggest approximating the ratio first, not trying to isolate for S. 10 multiplied by the sine of 50 degrees divided by 8 is 0.9576-ish. Strongly suggest drawing a sketch in standard position. The sine ratio is the ratio of y to r, so we're drawing a line where, a reference angles where our y value is about 95% of our radius. There are two possible values, one acute, one obtuse. Both, I believe, could fit in this triangle. One acute option, one obtuse option. Okay. I'll say that S1 is going to be about the inverse sine of 0.9576. I still have that number stored in my calculator, so I'll just ask for the inverse sine of that, and I get about 73 degrees. But without the ambiguous case of the sine law, this is just a grade 10 problem. Make sure that you use grade 11 math when you're writing a grade 11 quiz or a grade 11 test or a grade 11 exam. The second possibility for the angle S then would be the supplement. You can see it right here. Here's 73 degrees. There's the supplement of S1. 180 degrees minus 73 degrees, or about 107 degrees, which will fit in a triangle with an angle of, wrong triangle, will fit in a triangle with an angle of 50 degrees. Okay, you take it from there, solve angle C, solve the other side length. The printed lesson has the full solution. Okay. Keep your eyes open for the ambiguous case of the sine law. Anytime you're using the sine law to solve for an angle, you should have warning bells going off. Use your calculator to find one solution, but it has never given us all of the solutions that we want, and it still won't later in this course.